Hi, today we're going to look on the last section of the thermal engineering, which is we're going to look for the combustion process. So in this chapter, we're going to look on the analysis of the combustion that involve, which is commonly we're going to look on the liquid fuel, and then some of the touch that we're going to look as well on the solid fuel as well. All right, so some of the chapter outline is given in this slide, which is firstly we're going to look on the theoretical analysis, which is look on the fuel mass balance combustion equation, stoichiometric and then the non-stoichiometric analysis, which is initial stage. We're going to look on the theoretical aspect before or prior we go to the analysis of the combustions. So in the second section of the chapter, we're going to look on the application of the first law of the combustion process, and then we're going to analyze the enthalpy of combustions, and then to generate or to calculate the amount of the energy produced from the combustion process. So before that, we go to the combustion process, which is involved with the involving with the mixture of the component, where mixture of the substance that has two or more components in forming the air, where each of the components have their own properties, which is provided by the mole or mole fractions, and then as well we also can evaluate through the molecular weight, and as well to look on the gas constant that is represented by each of the substance of the gas mixture. So the mole fraction can be analyzed by calculating the Y, which is described the ratio between the number of mole and number of individual mole, where I is the individual component and M is the number of mole for the mixture. So for example, if you have the number of mole for oxygen is the number 1 mole, okay, and then mole of mixture for the dry air, let's say, is equal to 4.76. So the Yi or mole fraction for the oxygen is equal to 1 divided by 4.76, which is give you about 21%. And we also can calculate through the mass fractions, which is mass fraction is the ratio between mass of the individual component or individual substance divided by the mass of the mixture. So the total number of molecules and mass is the summation of each individual component. So for example, the number of mole for the mixture is equal to number of mole component 1 plus number of mole for component 2, number of mole for component 3, and blah blah blah. And as well for the number of mass for the mixture, which is given by mass for substance 1 plus mass of the substance 2 plus mass of the substance 3 and the other substance. So thus our molecular weight can be calculated from this correlation, where the molecular weight of the mixture is the number of molecular mass times with the number of mole divided by the number of mole for overall or for the mixture. And then the mixture of the gas constant, which is given by the R equal to R H divided by the molecular mass for molecular mass of the substance. Okay, So R is the universal gas constant, which is given by value of 8.314 kilojoule per kilomole Kelvin. So thus, if you have the if you want to calculate the gas constant for dry air, which is the M for the air is 28.97 kilojoule, kilogram per kilomole. So if you divide 8.314 kilojoule kilogram kilomole Kelvin divided by 28.97, so it will give you 8.314 divided by 28.97, so it will give you give you about 0.287. So this is a kilojoule per kilogram Kelvin. So this is a this is a gas constant for the dry air. So if you want to calculate gas constant for the water vapor, where the molecular mass for the water vapor for the water is 6H2O, which is about 18. So 8.314 divided by 18, 8.314 divided by 18, which is you get about 4619. Okay, 4619. So if you want to calculate this gas mixture, then you can determine what is the molecular mass for the substance. Okay, so ideal gas, if you imagine that you have a volume, okay, a tank, a volume, okay, which is this tank volume is a contain of the it's a mixture of several gases, okay, which is I will name it as I, which is J, K. So this is a mixture of the gas components, where each mixture will present, they will bring their own presentation of the pressure I, and then pressure J, and then pressure K. So the fraction pressure for each component can be determined by Dalton's law model, which is it is given by the number of the ratio of the individual pressure divided to the total pressure of each component, where total pressure of each component is contributed by Pi plus Pj plus Pk plus blah blah blah. So if you want to calculate the fraction pressure for the Pi, which is P given by Yi, which is equal to Pi over Pm. Okay, so this is for the fraction for the Pi, and then if you want to look for the fraction for the Pj, then you can just substitute this. And then each of the component of the gas or the substance also be presented by the volume, okay, which is volume for the I, and then volume for the J, and as well for the K, if you assume in that way. So each of the component also can be presented through the Avogadro's law, where through the Avogadro's law, the presentation of the fraction is throughout the volume fractions. So which is volume from the component I divided by the fraction Yi is given by the volume Vi divided by Vm. And then all of this, if we look on if we take the ideal gas equation, which is PV equal to RT, or PV equal to nRT. So which is we will get come up with these correlations, where the fractions, the mole fractions, is given by the Pi over Pm, and then Vi over Vm, which is the presentation of the mole fractions. So the theoretical, which is we're going to implement this toward our final calculation later on. So the definition of the combustion can be presented as the chemical reaction during which is a fuel is oxidized and a large of energy is released. A microscopic process to convert the stored chemical energy into useful heat energy. So the primary component required for the combustions is the fuel, oxidizer or oxygens, which is obtained from the from the air, which is the air is presented by this is a dry air, which is the component of dry air is N2 plus with the O2 and plus with the other gases, where the N2 is about 78% of the dry air and O2 is about 21% of the dry air, or the fraction Y for the N2 is 78 or 0.78 and Y for O2 is about 0.21. So the fuel is any material that can release energy when it is oxidized, and then it is consists of the hydrocarbon, and then it exists in all phases. It can exist in the liquid, it can exist in the solid, and then as well also it can exist as a gas. So common hydrocarbon fuel such as gasoline, which is CH18, which is presented the hydrocarbon which is CN plus CNH to N plus 2, and then also diesel, or known as the dedocane. Methane is another clean energy that been highly focused nowadays. It is very light, but it required with the combustion process, we produce quite high temperature, and then as well the LPG and CNG. Okay, so oxygen is 20.9% or about 21% of the contain, and then nitrogen about 78.1% and 0.9% of argon and other gases. So which means that each of the 1 mole of the oxygen consists of 3.76 mole of nitrogen. So which means that 1 mole of O2 plus 3.76 mole of N2. Okay, so for the dry air mole, which is 1.1 plus 3.76, which is equal to 4.76. So this can be neglected, or if you want to be more precise, you can calculate for the argon, 4.76 mole. Okay, so at the ordinary combustion, where the combustion is less than 1400 degrees Celsius, the nitrogen does not react, so that the nitrogen will be not react in the air, so it does not produce the NOx or nitrogen oxide. So when the combustion is above than 1400 degrees Celsius, the NOx is produced, which is about So another important criteria that you need to understand: a complete combustion only produce CO2, H2O and N2. However, the incomplete combustion will produce carbon monoxide, methane and methane is very harmful to the ozone layer. And then number C, so this is all greenhouse gases, okay, except for this is also greenhouse, yeah. And then air is also contained as a water vapor. With the water vapor, as we have seen before, the atmospheric air is combination of the moisture plus with the dry air. So a complete analysis for the combustion must also consider with the moisture. So how to do the analysis for the moisture combustions? We have to consider as well the the theoretical or the amount of the moisture content in the atmosphere. So hydrogen will complete burn to H2O, and then So this is a self-ignition temperature. So self-ignition temperature occurs when it will make the fuel to have a self-ignition when it achieves at certain temperature, at the SIT, self-ignition temperature. So self-ignition temperature for the gasoline is 260 degrees Celsius, carbon 400 degrees Celsius, hydrogen 580, carbon monoxide 610, and methane is 630. So what happened in this self-ignition temperature is that if you have a combustion chamber, or this is a piston, okay, so this is a combustion chamber, and this is your piston ring, and then this is your valve. Okay, so let's say that during the compression process, okay, in your four-stroke engine, during your compression process, so some part of the during the compression process, the pressure will be increased, and as well the temperature also will be increased, because PV equal to constants. Okay, so PV gamma equal to constants. Okay, so and then if you take PV equal to RT MRT, so this is what you get, which is actually the temperature also will be increased in that case. So some of the area which is the distribution of the temperature across the combustion chamber is not homogeneous. So some of the area will achieve the combustion temperature will be getting higher. So thus what will happen is that, for example, is this area achieve higher temperature, so the combustion will begin in this location, and that's where this location. So a small combustion will spark, and then will generate another combustions, another will expand that combustion into the other areas. So this will create what we call as the wave or shock wave, because a combustion also will create another pressure rise in the cylinder. So what will happen is that it will create a shock wave inside of the combustion chamber, and will increase sudden pressure for our combustion chamber. So if this sudden pressure increase very high, it increase to the certain numbers, and then your combustion chamber of your cylinder block cannot retain with the pressure, it will create what we call that as the or it will damage your piston or your combustion chamber. So what will happen here is that your engine will be damaged. Okay, so the phenomenon is called as the knocking. Okay, so this phenomenon is known as a knocking. So throughout the process, it will produce knocking sound, which is produced like it's like it's like a knocking sound. It's like some knock in your engine. Okay, so for a certain period of time, it will damage your engine operations. Okay, so another important aspect in the combustion analysis is that it is a content of the reactant plus with the oxidizer, or reactant which is come from the fuel, and then oxygen contained which is from the air. Okay, and then it produce the product plus with the heat. but the number of atoms and mass of the element must be equal from the both sides, left and right side. So this is the left side reactant, and then this is the product, which is on the right side. But the number of mole for each element on both sides may not be equal. So this is referred to the balancing combustion chemical equation, which is the reactant and the product. So this is happen in the combustion chamber. For a complete combustion, which is the product already well known, CO2 plus H2O and N2 if applicable. So C3H8 plus 5O2, this is a chemical balance between the reactant and the product. So this is the C3H8, and then it required 5 kilomole of O2 to produce 3 kilomole of CO2 plus 4 kilomole of H2O. So in complete combustion, in order to calculate the incomplete, to analyze the incomplete combustion, first we set the number of mole of the fuel to equal to 1, and then assume the fix of the possible substances in the product, and then write down all the mole numbers for the fuel, air, and a certain product, and then set to unknown mole numbers with the letters of A, B, C, X, and Y. So which is actually we're going to do this in the class during the class sessions. Yeah. So for example, if we have C3H8 plus with the dry air O2 plus 3.76, and then if we produce we do the chemical balance for that one. Okay, so another important criteria is to analyze the air to fuel ratio. So firstly we have to set the number of the fuel equal to 1, and then air to fuel ratio is the ratio of the quantify the amount of the air and fuel that exists in the combustion process, which is expressed in the mass basis. So air to fuel is equal to mass of air divided of the mass of fuel, or fuel to air ratio, which is mass of fuel divided to the mass of air. So where m is equal to number of mole times with the molar mass. So another important criteria known as the equivalence ratio, but in the engine analysis, this is known as the lambda value. Okay, so this is known as the lambda value. So applied to measure the amount of the air which is actually supplied to the combustion process, which is the equivalence ratio is equal to phi air to fuel ratio actual divided by the air to fuel ratio symmetric. So this is one of the example. You could do it. You can do it at the home. Okay. And then for stoichiometric theoretical air combustion, the minimum required air to complete the combustion to occurs, which is when a fuel is burned with a stoichiometric air, there is no unburned fuel and free oxygen exists. For example, for the methane, CH4 plus ATH, O2 plus 3.76 produce CO2 plus 2 H2O plus 7.52 N2. So we're going to do this the analysis during the synchronous class. When the excess of air, the term of the used to be air is supplied greater than stoichiometric air, or 0% excess air is equal to 100% of the stoichiometric, or 50% of excess air is mean that about 150% of the stoichiometric air. So another term is that when the air starving or air deficiency. So air combustion is supply is less than stoichiometric condition. It is known as the air deficiency of starved air. 10% starved air is equal to 90% of the stoichiometric air. Air deficiency is commonly practiced in industry when converted into gas fuel. So this is what we call when the combustion or the engine operating, especially for your engine internal combustion engine operated at the high RPM. So when engine operated at a high RPM, the temperature of the engine will be getting higher. So what will happen is that the fuel will be injected more than its normal condition. So with this, if we go into the stuffed air condition, so what will happen is that it will deteriorate the combustion efficiency and lower down the temperature for the internal combustion engine. So in order to analyze the combustion product, theoretically to achieve the complete combustion required to supply of the excess air. Actual cases, even the supply excess air fails to ensure complete combustion because it is almost impossible to predict the exact composition of composition product on the basis of the mass conservation alone. So in practice, usually we have to use the gas analyzer, which is located downstream from the combustion chamber or in the exhaust pipe, and then we calculate or we measure the amount of the product that being produced. So we do the reverse combustion analysis, and then we calculate amount of the required chemical combustion. So the effect of moisture in the combustion. So if the dry air is used combustion, so only this equation will be used. But however, if there is a effect of moisture when there is a humidity is involved, or in other cases when the moisture content is significant, which is the combustion operated in the high humidity, then we have to consider with the combustion. So which is O2 plus 3.76, which is the dry air, have to consider with the moisture. Okay, so the number of N of the dry air can be calculated by using the PV over P total, which is PV is the partial pressure of the dry air, and then PV is the partial pressure of the moisture at temperature. Okay, so where PV you can connect with the relative humidity, which is PV over P atmosphere. Sorry, PV over PG at temperature. Okay, so phi equal to PV at temperature, where PV is equal to phi times at PG at temperature. Okay, so then you can calculate the number of mole or mole ratio for that conditions. So ethane, okay, so this is another example. So we will do this during the class. And then this is natural gas. Okay, also good example that we're going to discuss later on. And then as well, this is octane. This is when we put as the volumetric analysis for the product. Okay, so then next we're going to look the energy analysis of the combustions. So previously it's just the combustion analysis. So this is the energy analysis of the combustion process, where thermodynamics point of view, the amount of the heat energy released during a combustion process is the important aspect to study. So we're going to use with the first law of thermodynamics to calculate the energy released from the combustion process, which is coming from the chemical energy contained, which is the changes of the energy system, is the changes of energy state plus changes of the chemical energy. So in energy analysis, the standard reference for the defined 25%, so we're going to use a standard reference at the 25 degrees Celsius at 1 atmosphere. So the property value at the standard reference state is referred as the H0, S0 and U0. So enthalpy of the reaction, or Hg, for the different enthalpy of the product at the specified state, and the enthalpy of the reactant at the same state is in the complete combustion. So the enthalpy of the combustion is the product, or is the summation of the enthalpy of the product minus enthalpy for the reactants. So enthalpy of each product, or we can put like that. Okay, so in energy analysis, the standard reference is defined by at 25 degrees Celsius and 1 atmosphere. So the enthalpy of formation is the enthalpy required of a enthalpy of a substance at a specific state due to the chemical composition. So it gives you the information of how much energy is required, or how much enthalpy is required to form the substance. Okay, so the enthalpy of the combustion for the chemical composition is given by H product minus H reactant, or given by this calculation. Normally N2 and O2 considered as a stable element, thus the enthalpy of the formation for this element is equal to 0. So in actual combustion process, the temperature of the reactant and the product are not at the standard reference state. Then the heat value of the reactant or product at elevated temperature state can be written by H component, which is given by this analysis, this equation, which is this is the enthalpy of formation. So this is enthalpy at temperature, and this is enthalpy at reference state. So enthalpy at reference state is equal to 25 degrees Celsius. So if you look, this is a Hertz value, which means that the symbol is in terms of per kilomole. So this is a per kilomole, and then this is a symbol for the reference state. So enthalpy of formation is also referring to the reference state. So this is enthalpy for the reactant. Then you have to calculate first, the process is that you have to do the chemical balance. Okay, calculate, and then you do the chemical balance for the reactant and then for the product. For both, which is if it is involving the theoretical combustion, then you do the theoretical combustion. But if it is also involving with the actual combustion, and then after that you do with the actual combustions. Okay, theory and actual. Okay, and then after that you calculate the air to fuel ratio, and then number 3, you calculate the energy. The energy is you have to calculate for each component of the substance. For example, oxygen, nitrogen, and as well the fuel, and for both reactant and the product. Okay, so this is another example that we're going to discuss in the class. Okay, then this is your assignment 1 and assignment 2. Okay, so that's all for the today class. We're going to look more details in or during the synchronous class. So thank you very much.